Problem number 49, we are given the percent compositions of a compound and we are asked to find the empirical and molecular formulas. So if we assume that we have a 100-gram sample of this compound, then 58.8 grams of it would be carbon. And we can do this because the percent composition is an intensive property. So it doesn't matter how much of it you have. And so we say that we have 100 grams because that just simplifies the computation. And we're going to convert that into moles. To change grams to moles, we're going to use the molar mass, and that's from the periodic table. And so I got that down here. Carbon has a molar mass of 12.01. Grams per mole. Grams of carbon canceled out. 58.8 divided by 12.01. And we don't need to go crazy with the precision here because it's going to turn out to be pretty close to a whole number is what we're looking for when we get to the mole ratios. So this is going to be 4.89 or 4.90. Let's just get 3. Three significant figures. Now let's do the same thing for the hydrogen component. If we have 100 grams of it, 9.8 grams would be hydrogen. And so let's convert that to moles. Again, molar mass is right off the periodic table. 9.8 divided by 1.008, 9.72. So if we have a 100-gram sample of this, we'd have 9.72 moles of hydrogen and 4.90 moles of carbon. And finally, for the oxygen component, if we had a 100 grams sample of this compound, we would 31.4 grams of it would be oxygen. So let's convert that over to moles. Oxygen has a molar mass of 16 grams per mole. Again, that's from the periodic table. (31.4) divided by 16, 1.96. All right, the next phase of this problem is we're going to take the smallest mole and see how many times it goes into every one of them. And the reason why we're doing this is because we can't have formulas with decimals in it. So when we do this, we're guaranteed to have at least one of them be a whole number. Hopefully they'll all be whole numbers, but at least one of them will be. And that's going to be the one that you're dividing it into itself. So this is going to be 1. And hopefully the other ones come out very close to whole numbers or whole numbers. All right, so for the carbon, 4.9 divided by 1.96, 2.5, that's fine. 9.72 divided by 1.96, and that's close enough to 5. Now, you don't want to round 2.5 up to 3. It should be very, very close to a whole number, or a half, or maybe a third, or maybe even a fifth. But those are generally the ones you'll see. So we need to multiply through by 2 because right now the way our empirical formula looks like is C2.5 H5O1. And so this is a problem we need to multiply through by 2. That way we'll have the lowest whole number ratio, and that's what an empirical formula is. So our empirical formula is going to be C5H10O2. And we're unable to reduce that. So there's your empirical formula. So we answered the first part of the question. Oops. Now let's answer the second part, which is the molecular formula. In order to get the molecular formula, we need to be given the mass, the molar mass, which is given here. And so the molar mass is 102. So we want to see how many times the empirical formula mass goes into it. And that's how many times we're going to multiply the empirical formula to get the molecular formula. So the empirical formula was C5H10O2. And so we get the mass of this is going to be 12 times 5 is 60, plus about 10, plus about 32. And so that's going to be 70 plus, that's 102 grams per mole. And that's going to be your empirical formula mass. And notice it goes into it one time. Therefore, the empirical formula is equal to the molecular formula. So the molecular formula is the same as the empirical formula, C5H10O2.